Welcome to this presentation of SNOW, in which we will give a first introduction of our research on goal-directed perception. And let me first give a brief summary of SNOW. SNOW is a 4-year project at TNO that is part of a larger program on applied AI. Here we study the combination of data-driven AI with knowledge-driven AI. SNOW consists of some 15 to 20 scientists from TNO and is extended with some 5 scientists working at our academic partners. The goal of SNOW is to create autonomous robots, which are robots that require fewer interventions than their remotely controlled or automatic counterpart. Though more complex environments will also increase the number of interventions, also for autonomous systems. We assume that the next set of robots will operate in an open world as part of a team, which means that the environment in which they operate goes from a static and predictable to a dynamic and unpredictable environment, that the robot will go from a single-purpose system to a multi-purpose system, and that it will operate in cooperation with other robots and other human team members. The research of SNOW is always showed in real-life demonstrates and experiments, also goal-directed perception. The research application of SNOW focuses on mindful inspection. In order to understand what is mindful, let us first look at existing solutions and robotic services. Current inspection robots take recordings at pre-programmed viewpoints in the plant, along a predefined or pre-programmed path. These recordings are then sent to a cloud service running some predictive maintenance software. When the battery charge of the robot is below some threshold, it is able to find its way to the nearest charging station. Hence, it is a standardized procedure not requiring much intelligence of the robot, merely automation. And it's a pity, as depending on what results after inspecting a point of interest, the robot is more efficient if it first tries to understand why a result is different from what was to be expected. The robot should be able to respond to the findings it gained during the inspection. It should understand whether or not it needs to gather more information in order to understand the situation, and where such information can be found, and whether or not an alarm should be raised. The 2 examples below illustrate the use of a mindful inspection, for which we will assume that the robot is tasked to inspect a manometer and then return home. Once the robot moved itself in front of the manometer, it will read its value, which reads that the pressure is too low. Instead of continuing to return home, the robot should first figure out why this pressure is too low by acquiring additional information that might reveal why this pressure is too low. Perhaps it is a leak or a pump that is not functioning properly. In any case, it would be very useful to understand what is going on and why the pressure is too low. Once the robot returns home, that's the second example, an anomaly is detected in the floor. In this case, a huge hole and broken tiles. The robot should not ignore this, but instead try to understand what type of event may have caused this anomaly. Was it a small object with sharp corners that could have caused the leak, or was it a bulky object that not only broke the floor, but also other pipings? Again, the robot should gather more information about what happened so that a proper follow-up action could be suggested either to the robot or to the plant operator. So in general, the challenge of goal-directed perception is to deliberately plan which information is valuable and whether this information could be of use to the robot when it is trying to understand what might have happened. Our research on goal-directed perception is part of a larger system, so that this entire system is able to complete actual inspections in real-life situations. In order to decompose the topics within this goal-directed perception, these topics will result in modules that should be placed within this setup. This setup contains an ultrasonic array and an RGB camera for imaging, it has the Spot robot as a robotic platform, and it has some gas sensors for general measurements. All these are managed by agents that run services such as GoTo and Acquire Image. These agents are scheduled by a behavior executor along with services shown on the right for processing such sensor data into actual information about the external environment, so that our robot will exhibit a set of desired behaviors. An example of such a behavior is to inspect the manometer located at some XYZ position, of which the result will be stored in the upper part of the knowledge base, characterizing the situation. For experimenting our progress in goal-directed perception, there are three parts of this setup important. These are the knowledge-driven anomaly detection on the right, to detect that something is out of place. Then, in the upper part, we have common sense and reasoning to postulate what events might have taken place for the anomaly to be realized, and further indicate what actual observations might provide evidence that could either falsify or back up this postulated event. Finally, on the right, we have active inference to plan which observations, as pointed out by the reasoner, is most effective to acquire first. In the next slides, Gert-Jan will introduce our ideas on knowledge-driven anomaly detection.
My name is Gert-Jan Berghouts. I'm part of the SNOW team. My responsibility is the perception part. Specifically, knowledge-driven anomaly detection, to understand when Spot encounters a situation that's wrong, or either to understand how to act somewhere. Starting with defining when something is wrong. For instance, tools should not be left on the floor because they are abandoned objects and Spot can triple over them, or they might indicate a hazardous situation. And there should be no water on the ground. For instance, Spot might slip. To have such reasoning, it involves relationships between segments and objects in the scene. But there are very many types of variations of tools, and standard object detection might not suffice. Also, floor and water are not crisp objects or segments, so a standard object detection model or an image segmentation model might fail. What's more, in an industrial plant, there are many types of objects. That means that there are a lot of hypotheses. That's really hard to deal with. So these are a number of challenges that we want to solve. And moreover, we also want to be able to quickly adapt from one situation, like the tools on the floor, to another, like water on the floor. Our method is to define such situations of interest symbolically. And preferably, we don't want any retraining. And in this scenario, we also found a model which doesn't need any retraining at all. Let me explain to you what our method is. So first we have a question, is there a tool on the floor? To be able to detect it, first we define it by first order logic, which is really expressive and therefore suitable for our purpose. So here we define an object being a tool on the side of something which is called a floor, and it should also be above the floor. So this represents Spot's perspective on the scene, finding tools that are abandoned on the floor. To understand what is there in the scene, we need to have perception. For that, we use zero-shot recognition. We don't want to retrain, we want to leverage what's already there. We do so by a model called CLIP. It's a language vision model, and it enables us to translate a search query like tool or floor into things that we can recognize in the images. So in the end, we have a model that can translate an image into symbols. The next step is to have neurosymbolic reasoning. So now we can combine the logic and the things that we saw in the images, and we have logic rules to understand whether the situation that we're interested in is really happening. For that, we need also some helper functions, like what does it mean to be in between of something or on the side of something, and then we can reason. For the reasoning, we need probabilistic facts, which we extract from the heat maps. So here you saw the image to symbols heat maps, and from that we extract probabilistic facts. For instance, that the probability of tool at position 3135 is 87%. Combining those probabilistic facts with the logic enables us to understand that the probability of tool on floor here is high, and so that a hazardous situation might actually be occurring here. Here are some results. So you can see indeed that the model was able to detect that in this image there are tools on the floor. You can see that by the hotspot in the heat map. And it was based on the underlying images that were extracted for floor and tool. So these are the probability maps for those two concepts. You can also see some other nice results here for the hammer on the floor and also for some other tools on the floor. And essentially that's because they are indeed detected as tools and also on the floor. So the spatial configuration is the way what we search for. But there are also some other interesting cases, like here. This is also understood by the model as tool on floor. And why does that happen? Because actually the tools are on the cabinet and not on the floor. What happened? So the Gazelle logo on the cabinet was detected as a tool because it was associated as such. This is a bias in the language vision model we use. So this is a flaw in the zero-shot recognition, and that propagates into the reasoning. A similar thing happens on the right. So you can see that on the box on the ground, there's actually some duct tape, which is associated with tool, and it's right above the floor. So the model reasons that indeed these are tools on the floor. Well, actually these are flaws. Okay, so what happened here? Because these are false negatives. There are tools on the floor, but not detected as such, because there are no hotspots in the heat map of the result. So what happened? Well, floor is detected well, but tool is not recognized as such. I think this is because it's a really niche tool. So it's a flaw in the language vision model that it doesn't understand that this is a tool too. On the right, you can see that the tool was detected, but the floor was not detected as such. Maybe it looks more like a wooden plate, and context is lacking for the model to judge that this indeed is a floor. Okay, so here are a number of nice examples that are illustrating the hard cases. So here there are a lot of tools. There's also floor, but the tools are not on the floor. And the model correctly recognized that in fact the spatial configuration is not tool on floor. So this is a correct judgment. And on the right, the same thing happens. So there are a lot of tools, but they are all on the table or on the surface and not on the floor. So the spatial configuration is not what we're looking for, and these are not hazardous situations. To summarize, I believe that neurosymbolic reasoning is a valuable tool for this kind of situation understanding and to have knowledge-driven anomaly detection. We can represent the user's interest via symbolic rules, so we can quickly adapt, and we define them by relationships between the entities. The tool we are using is a Python tool called Scallop, published at NeurIPS 21, and it seems very useful for our purposes. First results for the snow use case seem promising. That's the end of my part. I hope it was interesting to you.
Our second topic within goal-directed perception is common sense and reasoning, which could also be seen as one topic, aiming to understand the situation around us. So we have a situation given, and something in the situation triggers our attention. For example, a pressure that is too low or broken tiles on the floor. We need to find out what happened, for which possible events are postulated from our knowledge. Might a cat be related to this pressure drop? No. Might a pump be related to it? Perhaps. Is there evidences for such an event? Well, first we should figure out which pumps are relevant, which means if we know which pipe segments link a pump to this meter, then we know which pump to further inspect. Then, a pump that is not powered on or worn out might result in a lower pressure than normal. Is there evidence for that? This decomposition continues until actual evidences can be observed by the robot from the environment. And based on that, we might understand or we might reason whether this postulated event is in fact the cause why this pressure is dropped or why the situation is as it is. There are two scientific fields related to our work, which are knowledge representation and reasoning. Knowledge representation is about the structuring of information, either done on process level using first order logic or using descriptions such as ontologies. Reasoning is about processing actual information or inference. It can be done using Bayesian networks, such as using Bayesian theory and probability theory, or an alternative is fuzzy cognitive maps using some fuzzy logic. These last two on reasoning are part of a larger topic called evidence theory. Both these topics will be presented in the next few slides in more detail and how we use them. Ontologies are about the nature of beings. Typically, you start with some kind of a taxonomy of concepts in such an ontology, describing the hierarchy between them. Then, in addition, you will have attributes and values and relations specifying the meaning of the different concepts. You can represent ontologies as conceptual graphs, or you can represent them as frames. The example here is shown in frames. The benefit is they are machine readable or queryable, which means that they are a way to represent knowledge in your system. The example that you see here is that there is a pipe, which is a specification of a flow artifact, defined by this sub-relation between pipe and flow artifact. Flow artifact is in itself a specification of artifact, also defined by the sub-relation. And because artifact has a position xy, flow artifact inherits this position xy, and also pipe, which is a specification of flow artifact, will inherit this property or this attribute, position xy. In addition, the pipe also might have meters installed on it. And whether that's the case is defined by this relation is on. In this case, this relation is to some kind of a manometer, which is a specification of sensor. And since sensor is a specification of an artifact, and because of some clarity I did not define the concept of a sensor over here, so the dotted line between manometer and artifact is actually a sub-relation going from manometer to sensor to artifact. Now, and since artifact has this position xy, also the manometer has a position ny, but in addition, the manometer might also be installed on a pipe. And that information is being characterized by the relation between this manometer installed property and the pipe meters property. Now, in this example, more elaborate ontologies can be developed to model our knowledge in describing industrial plants. So if we were to understand the integrity of a pipe, how should we then extend the ontology shown before? Well, in this case, we included new concepts, for example, pipe, degradation, gas and rotating equipment, and we have some properties such as age, vibrations, noise anomalies, heaviness, rust, dent, leak, pressure, so on. And the pipe might have properties such as age and vibrations, but also pressure. And rotating equipment has properties, for example, how heavy it is, whether it is having noise anomalies that it never had before, and also age. There's one relation that I modeled over here, which is the green arrow, indicating whether the two concepts have an effect on each other. So in this case, whether rotating equipment has an effect on pipe. Therefore, the arrow points towards pipe. There is also a weight with each arrow, in this case a plus or a minus, indicating that the effect is likely to take place or not likely to take place. So in this case, if I have rotating equipment, then it is likely to cause vibrations. And the error also indicates that if my rotating equipment is heavy, or if I have higher anomalies on my noise, or if my rotating equipment is of an older age, then it's also more likely that these vibrations will be high and not low. Similarly, age of the pipe, if the age of the pipe is high, then it's more likely to cause degradations of any kind, being it dent, a leak, or rust. And vibrations is not really likely to have an effect on the degradation, not so much at least as the age. So in this case, it's more with a minus sign. And vibrations are only if it even has some kind of effect, it will have an effect on a dent or a leak, but not on rust. On the other hand, rust itself has an effect on creating a leak. Having more rust will imply that a leak is more likely to take place. Pressure now is related to a leak. So if there's a leak, then there's also likely to be an effect in pressure. In this case, to have a lower pressure. And also, if there's a leak, it has an effect on the gas that can be measured in the external environment, of course, which you don't want, but that's the result of a leak. So, now I'm ready to move my pointer. In case you want to know whether there's a dent or whether there's a leak, then this ontology shows what kind of evidences we might find in the environment. Evidence is related to vibrations of the pipe, evidence is related to gas measured in the environment, and evidence related to pressure drop. And based on those evidences, we can then come to a conclusion whether there's a leak or not. But for that, we also need some reasoning. There are many ways to reason using the ontology and sensor data is acquired by the robot, and one of them is evidence theory. Evidence theory makes an assumption on what is known and what is not known by the system, and various approaches exist for evidence theory, being Debye-Schaeffer, probability theory such as Bayes, and possibility theory, which is an extension of fuzzy. Now each of them has their own assumptions on what is known and what is not known, and in order to understand what they mean with that, we make use of this picture over here, where you see that there's this gray part, which is a representation of what is not only known, but also what is reliably modeled. So we have formal equations, formal models, formal rule of thumbs, representing the current state of our knowledge. The green one is knowledge that is not yet available. It's not yet even formalized in rules or anything, but it's also even not available. We assume that we at some point will achieve it, so it is evolutionary attainable, but at present day it's not there. The white box that is in between is knowledge that is still among us and that we have it. It's not just all formalized, which could be, for example, creativity or intuition. So if I see something I might have a solution to, that is not always formalized by a rule of thumb, but I know from experience that that my decision will have an effect and will have a good effect on it. So in that case, it's part of this white box. And now, of course, we should make a decision on which approach we think is suitable. Now, one of the easiest ones to rule out is probability theory, though it's a very, very useful approach, but it also assumes that all knowledge is formally modeled. And then in our case, it's not the case. So we have most likely many pieces of knowledge that are not formally modeled yet in rules or anything. So we need to make a decision between Debye-Schaeffer and possibility theory. And then there's a difference between those two is that Debye-Schaeffer requires crisp values, and in our case we don't have always crisp values, right? So how much is for example rust having an effect on that the leak is present there's not something that we can put a number on. And for that reason, possibility seems to be a better solution. Let me conclude this part on common sense and reasoning with some findings. So firstly, ontologies are useful to structure information and to structure evidences. And we can represent them as a graph, and graphs are also a useful tool to model cause and effect. So if we implement an ontology as a graph and we update it with the available evidences, then we have a very nice representation of the environmental state. We can then query this graph on all known evidences and how these evidences relate to one another, and exploit possibility theory to make a conclusion how plausible a leak or event is. We can then postulate which evidences that are not yet available, but if they might become available, how these would increase our certainty on whether there's a leak, yes or no. And if we can postulate such evidences and we can indicate how significant their value is for this conclusion, then a planner might make decisions on which information or which evidences to seek first and which one to seek after that.
My name is Erwin, and in this part of the presentation I will tell you more about the planning algorithms that we are currently studying and using in the SNOW project this year. As Joris already mentioned at the start of this presentation, we want to plan our actions in such a way that we can collect relevant information to achieve our goals. But now the question is, of course, how do we do that? Let's start with an example in the mountains. So when climbing mountains, you are planning your moves in such a way that it is likely that you reach the goal at the top. But in the SNOW project, this is of course slightly more complicated. So the main idea is that we start with a specification of the goals we're interested in. An example goal could be to reduce the uncertainty about an industrial area in which you are doing inspections. Another goal could be to return to a specific location before the end of the inspection time window. And what the planning algorithm actually does is taking all these goals as input and selecting the actions which can be executed by Spot. And this year we started to explore a new concept for this called active inference. And in the next few slides I will tell you more about that. Planning problems are typically formalized using Markov models, which define an agent that interacts with an environment. Here on this slide you can see an example at the top. In our project, Spot is of course the agent which takes actions in an industrial environment. And as a result of this action execution, the environment may change. Unfortunately, Spot doesn't always see the state transition directly, and instead it's just receiving an observation signal O and the reward value R. And what traditional planning algorithms try to do, like the ones that we used last year, they purely rely on this reward signal R, and they try to maximize that. This also means that you always have to construct this reward signal by hand based on a goal that you would like to achieve. In practice, this works well, but it's also relatively complicated to define sometimes. And if your goals and if your environment is changing, you have to adjust this every time, which is something that just takes time. And that's something we don't want to have, of course. This year we started to explore something new. It's called active inference, which is a concept from neuroscience that defines that agents naturally want to minimize something that is called free energy. And this free energy consists of two terms. First of all, it's important that Spot minimizes the entropy of observations. So in practice, this means that we prefer actions with limited uncertainty in the resulting observations. It's also important to take actions which lead to so-called preferred observations. So for example, this allows you to encode that Spot prefers to correctly infer the state of pipes in the industrial area. And we believe that active inference can be an important tool for SNOW because it eliminates the definition of a reward signal, which makes our planner more flexible, and it makes it also more easy to adjust in case the environment is changing. I can imagine that free energy sounds quite complicated, so I would like to illustrate active inference with a basic example. Suppose that Spot is performing an inspection at a damaged pipe, like the one that you see here on the slide, and initially doesn't really know that the pipe is damaged, so it needs to infer this based on inspections, such as the ones that Gert-Jan was discussing. And in this example, Spot can move closer to the pipe, and this results in more accurate inspections. And if our planner would consider this simple problem, we would expect that it first moves closer to the pipe, and after that it starts to perform inspections. And in my next slide, I will show you how active inference actually models this and how it chooses this action first. So first moving closer to the pipe, and then after that performing an inspection. This slide shows the planning tree that is being created. And let's assume, just in this example, that the true state of the pipe is damaged. Basically, there are now two different options. So Spot can decide to inspect immediately. And in this case, the camera may be less accurate, which means that Spot sometimes thinks that the pipe is damaged. And sometimes it thinks that the pipe is not damaged. And in this path of the tree, the expected free energy is relatively high because there's uncertainty in the observations and the final conclusion is sometimes just wrong. There's also another path that Spot is able to follow in this planning tree. So that's first moving closer, and then after that it does an inspection. So in this case, the inspection always leads to the correct judgment that the pipe is damaged. And this path has free energy that is much lower because the uncertainty in observations is limited. There is no uncertainty because it's always getting the information correctly. And the final conclusion about the state of the pipe is also correct. So basically that means that the path with moving closer first is always better in this planning tree because the expected free energy of that path is lower. And what the planning algorithm tries to do is just evaluating such paths in a tree, and it prefers the paths with lower expected free energy. And in practice, of course, this tree can be much bigger, but this basic example shows you for the example problem that I introduced, how it's actually choosing the action first to move closer, followed by the action to do the inspection. In this final slide, I will briefly show you how active inference integrates in the planning algorithms that we're using. In Spot, we use Monte Carlo tree search, which reasons based on beliefs over states, and branches in this tree correspond to actions and observations. And it turns out that free energy can be computed with this relatively complicated formula that you see here on the slide. But the main message is that it's relatively easy to modify the planning algorithms that we use. So we are currently just modifying the algorithms that we built last year. We just remove the reward signal that it uses, and we integrate free energy based on this formula. And the result is that we get a planning algorithm that actually plans with free energy as a reward function, rather than having the hand-defined reward values. In addition to this, we are also currently working on a few test cases to illustrate the potential for snow even more. And Joris will tell you a little bit more about that in the next slide.
We complete this presentation with a small example on how our three topics, knowledge-driven anomaly, common sense reasoning, and planning with active inference, how these three work together in a mindful inspection use case. For that, we have a pipe which is connected between two pumps. In between, or in the middle of this pipe, we have a valve, splitting this pipe in two sections. Each of the sections has a particular pressure that can be read out by a manometer. Now the robot is able to move within the area and conduct one of the 5 inspections, either reading out the power of the pumps, reading out the pressure in the pipes, or reading out the status of the valve. Now suppose our knowledge-driven anomaly has detected broken tiles somewhere in between area 1 and area 3. Then this will be stored in the knowledge base, and the common sense and reasoning will pick up this knowledge or this information and reason with that, and may think, hey, if there's broken tiles, then might also be the case that my pipe is broken and that there's a leak. If there's a leak, what kind of information is most valuable to me to draw that conclusion and to be certain about it? And I might come to the conclusion that reading out manometer is the most valuable piece of information, but if that's not doable or attractive, that either the pump or the valve can be inspected as well. The planner then computes the free energy for each of those inspection actions, and it might come to the conclusion that actually B2 is the one that is most attractive as well. So it will send the robot to inspect B2, and it might come to the conclusion that B2 is normal, so pressure is normal and all is well. There's also no leak, but it might also come to the conclusion that actually the pipe is under high pressure or under low pressure, and if that's the case, then more information is needed to draw the conclusion whether this pipe is leaking, yes or no. And then common sense reasoning will suggest new types of information or new types of inspections to the planner, which will then plan the next attractive action, up until common sense reasoning says, I'm now very certain that this pipe is leaking or is not leaking, and somebody will be notified about it. So with a small example, we try to show the benefits of mindful inspection according to our methods on goal-directed perception. This was our presentation on goal-directed perception and how it may be used in mindful inspections, so that once particular information or every events have been detected in the world, that the robot is not ignorant and continues its inspection, but stays put and thinks about what other types of information are valuable and should I gather in order to understand the situation. I thank you for your time and hope to see you soon.